Graphing polynomial functions. We're going to go through a series of steps for graphing a polynomial function. We'll determine the end behavior, we'll find the x and y intercepts, we'll determine the real zeros and their multiplicity, and we'll use this information to determine whether the graph crosses or touches the x-axis at each x-intercept. We'll determine the maximum number of turning points, and we'll use all of this information to draw a complete graph. And if we need to, we'll find additional points on the graph on each side of the x-intercepts. So let's graph f of x equals 2x plus 1 times x minus 3 quantity squared. So for end behavior, we need to find the degree. We have a factor that's squared, we have a factor that is linear, and if we were to multiply them out, we're going to get a polynomial that has degree 3. We have a leading coefficient in one factor of 2, and in the other factor is 1. So 2 times 1 times 1 is going to give us 2, which means our leading coefficient is positive. So our end behavior will be down and up. For our x-intercept, we will set each factor equal to 0 and solve for x. So 2x plus 1 equals 0, x minus 3 equals 0. Solving for x, we get x equals negative 1/2, and x equals 3. So we have two x-intercepts, one at negative 1/2, 0, and one at 3, 0. The y-intercept, we need to find f of 0. So we will substitute 0 in for x, 2 times 0 plus 1 times 0 minus 3 quantity squared. That simplifies to 1 times negative 3 squared, which is 9. So we have a y-intercept at 0, 9. This first factor had an exponent of 1, so it's a linear factor. The second factor has an exponent of 2, so our graph behaves like a quadratic at the second x-intercept. The maximum number of turning points is found by taking n and subtracting 1. For this polynomial, n was 3. 3 minus 1 equals 2. So we have a maximum number of turning points of 2. Let's plot our x-intercepts, so negative 1/2, 0, 3, 0. Our y-intercept, we know that end behavior is down and up, so we have something generally in the shape of this purple graph. We know our graph goes through the x-axis at negative 1/2, but turns around on the x-axis at 3. So we get a graph that may look something like this. We don't know exactly where it turns around first after the y-intercept, but it could technically be on the left side of the y-intercept. If we really wanted to know for sure, we could try values of x in the function and calculate the function values. But for our purposes, this graph will work. Our end behavior was determined by looking at our degree and our leading coefficient. Our degree was 3, and if we were to multiply out our factors, we would get f of x equals 2x cubed minus 11x squared plus 12x plus 9. And this graph resembles the graph of y equals 2x cubed for large values of the absolute value of x. So what was important if we were to multiply out our factors is that first term, and if it's written in standard form. So the one with the highest degree, 2x cubed. Let's look at the graph of f of x equals x minus 2 times x plus 3 quantity squared times x minus 5. So looking at what our degree is going to be, we would have x times x squared times x. Multiplying out, we would get x to the 4th minus x cubed minus 23x squared minus 3x plus 90. So our degree is going to be 4. And the graph behaves like y equals x to the 4th for large values of the absolute value of x. So for end behavior, degree is 4, leading coefficient is positive. That means my graph will be up and up. It goes up and to the left and up and to the right. X-intercepts, let's set each factor equal to 0. X minus 2 equals 0. X plus 3 equals 0. X minus 5 equals 0. Solving for x, we get 2, -3, and 5. So we have 3 x-intercepts, one at 2, 0, one at -3, 0, and one at 5, 0. Let's plot those. So 2, 0, -3, 0, 5, 0. The y-intercept, let's find f of 0. So 0 minus 2 times 0 plus 3 quantity squared times 0 minus 5, or -2 times 3 squared times -5, -2 times 9 times -5, which is positive 90. So we have a y-intercept at 0, 90. So to graph this, I'm going to need to change the scale on my y-axis so that every grid line is worth 10. So 90 would be here. We know that this first factor was linear, so that x-intercept at 2, 0, the graph will behave linearly, as well as for that last x-intercept at 5, 0. That second factor had an exponent of 2, so at -3, 0, the graph will behave like a quadratic and actually turn around on the x-axis. The maximum number of turning points is n minus 1, so 4 minus 1, which is 3. So again, we know our graph is going to be up and up. It's going to turn around at -3, 0. So it could look something like this. Again, if needed, we could calculate more points by choosing values for x. Let's look at the graph of f of x equals -2 times x plus 2 times x minus 3 quantity cubed. So we have a factor that has an exponent of 3. So -2 times x cubed. That means our f of x will equal -2 x to the 4th, and so on. So ... So it's not important to actually go and multiply everything out to understand what the graph is going to behave like. All we need to do is find that first term. So this graph behaves like y equals -2x to the 4th for large values of the absolute value of x. The end behavior, we know that the degree is 4. The leading coefficient is negative because it's -2. So our graph will have an end behavior of down and down. It will go down and to the left and down and to the right. Let's find our x-intercepts by setting each factor equal to 0. -2 equals 0, but -2 does not equal 0. X plus 2 equals 0. X minus 3 equals 0. Solving for x, we get x equals -2 and x equals 3. So we have 2 x-intercepts, one at -2, 0, and one at 3, 0. Let's plot them. -2, 0, 3, 0. For our y-intercept, we need to find f of 0. So -2 times 0 plus 2 times 0 minus 3 quantity cubed, or -2 times 2 times -3 cubed, -2 times 2 times -27, which is positive 108. So again, I need to change the scale on my y-axis and plot the y-intercept of 0, 108. So it's up here somewhere, approximately. We know that this first x-intercept is linear because it has an exponent of 1. but the second set of parentheses has an exponent of 3, so our graph behaves like a cubic function when passing through this x-intercept. The maximum number of turning points is n minus 1, which is 4 minus 1, or 3 here. So let's try to draw our graph. We know that it goes through negative 2, 0. It does have a y-intercept, and at 3, 0, it behaves like a cubic. Right here, it's kind of like a cubic function. And this is important because technically there's no turning point there. It does squiggle a little in non-mathematics terms, but we're never changing direction. We're still always going down. So this graph technically only has one turning point. So it's important to note that we got the maximum number of turning points, but again, that's a maximum number, and it doesn't mean we will always have that number. Let's look at the graph of f of x equals x plus 1 quantity squared times x minus 2 quantity squared. So we have x squared times x squared. So in the long run, if we were to multiply this out, we would get f of x equals x to the 4th dot dot dot. So our graph behaves like y equals x to the 4th for large values of the absolute value of x. For the end behavior, our degree is 4. Our leading coefficient is positive, so our graph will be up and up, meaning up and to the left and up and to the right. To find our x-intercepts, we'll set our factors equal to 0. So x plus 1 equals 0, x minus 2 equals 0. Solving for x equals negative 1, x equals 2. So we have two x-intercepts, one at negative 1, 0, and one at 2, 0. Plotting them, we have negative 1, 0, and 2, 0. Y-intercept, we need f of 0. So substituting 0 in for x, we get 0 plus 1 quantity squared times 0 minus 2 quantity squared, or 1 squared times negative 2 squared, which is 4. So we have a y-intercept at 0, 4, which we can plot. This first factor is quadratic because it had an exponent of 2. That second x-intercept is quadratic as well, or the graph behaves quadratic there, has multiplicity of 2 because the factor had an exponent of 2. So the maximum number of turning points is n minus 1, which is 4 minus 1, which is 3 again. And because it's up and up, and our graph turns around at both of our x-intercepts, our graph could look something like this. Okay, so in our last example, this is not factored for us. So we're going to need to factor this in order to find our x-intercepts and to help us understand what the graph will look like. First, though, our first term is negative x to the 5th. So the graph of f of x behaves like the graph of y equals negative x to the 5th for large values of the absolute value of x. The end behavior, we need the degree, which is 5, and our leading coefficient is negative. So our end behavior is up and down, up and to the left and down and to the right. So for the x-intercepts, now we need to go back to our polynomial function and factor it. So if we look to see if we have a common factor that we can factor out of everything, we can factor out x squared, and because the leading term is negative, we factor out the negative as well. So dividing everything by negative x squared, we get x cubed plus x squared minus x minus 1. And this is 4 terms. So a way we can factor this is using factoring by grouping. So I'm going to split the polynomial in half. Looking at the first 2 terms, x cubed and x squared, what's the greatest common factor? That would be x squared. And if we divide both of those terms by x squared, we end up with x plus 1. If I look at the second half, negative x minus 1, what's my greatest common factor? 1, and because the third term is negative, we factor out the negative. Dividing both those terms by negative 1 gives us x plus 1. What's important is that the parentheses are the same, so we can factor that out, x plus 1. And then in my second set of parentheses, we will put those two greatest common factors we factored out, x squared minus 1. And we need to remember our original greatest common factor, negative x squared. Now, that last parentheses could still be factored because that is a difference of two squares. So, negative x squared times x plus 1, two sets of parentheses, the square root of x squared is x, the square root of 1 is 1, 1 gets a plus, 1 gets a minus. We do have two factors with x plus 1, so we could finally rewrite this as f of x equals negative x squared times x plus 1 quantity squared times x minus 1. Okay, so let's set each of our factors equal to 0. Negative x squared equals 0. X plus 1 equals 0. X minus 1 equals 0. Dividing by negative 1, we get x squared equals 0. Square rooting both sides, x equals 0. Technically plus or minus 0, but that's just 0. Second one, subtracting 1, x equals negative 1. Add 1, x equals 1. So we have three x-intercepts, one at 0, 0, one at negative 1, 0, one at 1, 0. Let's plot those, one at the origin, negative 1, 0, 1, 0. For our y-intercept, we need f of 0. So I find it easier to substitute it into the factored form, but it doesn't matter which form you substitute it into. So negative 0 squared times 0 plus 1 quantity squared times 0 minus 1, which is going to be 0 because we're multiplying everything by 0. So, and we already knew that we had a point at the origin, so the origin is our x-intercept and our y-intercept. Okay, so because we have an exponent of 2 on negative x squared, that means the origin will be an x-intercept where our graph will turn around because the graph will behave quadratic at that point. And the same can be said at the x-intercept at negative 1, 0. But our x-intercept at 1, 0, our graph will behave linearly and just pass through the x-axis. Pass through the x-axis there. The maximum number of turning points is n minus 1. That is 5 minus 1, which is 4. So we could have a graph something like this. Again, we don't know exactly how high up between those x-intercepts our graph comes. We could find some more exact points by choosing some values of x, for example, negative 1/2 or positive 1/2, and finding out what our function value is. But for our purposes, this graph will suffice.